Okay. Here is a photograph of a glass containing water and oil. And you probably know this from personal experience. You could shake this up, you could stir it, you could mix it up, and then as soon as you stop, it'll revert to being two layers again. Oil and water do not mix. And we want to know why. Why does that happen? There's something about the water molecules that causes them to bunch together, to clump up, and exclude the oil. The reason the oil is floating is because it's less dense than the water. But the reason that they're not mixing together has more to do with the nature of the molecules. And the clues here are electronegativity and polarity. So here's the Lewis structure for water. When you just look at the Lewis structure, you might think, oh, well, that's a linear molecule. But we have now learned that here, this oxygen has 4 groups, tetrahedral shape. Erase 2 of the corners, this has a bent structure, right? We see that oxygen and hydrogen are sharing a pair of electrons. When you share, it's not always equal sharing, right? My husband and I share a bed. We're married, so I guess that's not too unusual or weird, right? Is it always shared equally? No. The other night, he took up like 3/4 of it. And I'm laying on the side thinking, well, at least there aren't any children, and there's only the dog in bed with us, and the cats didn't join us, so it's okay, right? We're sharing, but it wasn't equal that night. Other times I hog the bed, right? So it goes back and forth. But when oxygen and hydrogen share these electrons, they're not always sharing equally. Oxygen hogs the electrons. It's like hogging the blankets, right? Always, oxygen takes the blankets, the electrons. Oxygen is more electronegative than hydrogen. So the shared electrons are more likely to be found near the oxygen than near the hydrogen. So electronegativity is defined as the ability of an element to attract electrons within a covalent bond. So they have determined the electronegativity of a bunch of different, pretty much all the elements. It's a relative scale. It's not something that can be measured absolutely. And so they said, well, we're going to say that fluorine is the most electronegative. It is the most electronegative. We're going to say that that's 4, and then we're going to measure everything relative to that. So we'll get a little more to that in a minute. So what happens with the unequal sharing is something like this. Oxygen is more electronegative. It's more attractive to the shared electrons than the hydrogen. And this is one of those cloud diagrams where if you took a picture, a multiple exposure picture of the atom, these little dots would represent where the electron was, the pair of electrons was at any given time. And we'll see that it spends more time over here than it does around the hydrogen. It's unequal sharing. Well, those shared electrons have a negative charge. And so if the electrons are spending more time over here, then this side of this bond is going to be slightly negative, and that side is going to be slightly positive. It doesn't form an ion. Hydrogen doesn't give its electron to oxygen, but the electron spends more time near the oxygen. So I think of this as a little bit like 2 little boys who live next door to each other. So those are the electrons. And they're friends, so they hang around together a lot. So we've got this pair of electrons. Here's hydrogen's house, and here's oxygen's house. At hydrogen's house, they've got a black and white TV and some old Thomas the Tank Engine videos on VHS. Like, who even has a VHS player anymore? If you're hungry, Mom will give you bread and butter and a glass of water. They don't even have an ice maker. It's just kind of pitiful if you think about it. Compared to over here, where they've gone a little bit nuts in the other direction. They've got the big screen TV, they've got every channel, every gaming system, there's a pool and a trampoline in the backyard. Mom will order you pizza. They have a soda fountain in the kitchen. Where are those 2 little boys going to spend more time? At oxygen's house. Why? It's more attractive, right? the shared electrons are more attracted to oxygen than they are to hydrogen because oxygen is more electronegative. I'll show you in a minute how we can predict which is more electronegative. So these electrons are shared. This is not where oxygen has adopted hydrogen's child. That would be an ionic bond, a transfer of the electron. This is shared. They're just going back and forth. Do they ever go over here? Yeah, they do, but they spend more time here. So there's a partial negative charge on this side and a partial positive on that side. That's called a dipole moment. It's a separation of charge within the bond. So it's not a positive and negative charge, but it's a partial. So we use this lowercase Greek delta. Looks like a D with bad posture. That means a partial negative charge and a partial positive charge. Any questions? So covalent bonds that have unequal sharing, a dipole moment, are called polar covalent bonds. Think about the North Pole and the South Pole. A compass points to the North Pole because there are magnetic fields on our planet that line up that way. The North Pole and the South Pole are on opposite sides and they're different. So a polar bond has ends of the bond that are different. One's slightly negative, one's slightly positive. How great those partial charges are depend on the electronegativity difference. So if you had, the houses that I described, hydrogen and oxygen, those are vastly different, right? Well, what if things were more comparable and the only difference between the two houses is that one house had the trampoline and the other house just had the swimming pool without the trampoline? So then the sharing would be much more equal, right? Because the one house is only slightly more attractive than the other. So it's the difference in how attractive those houses are that affects where the children spend more time. It's the difference in electronegativity that affects how unequal the sharing of the electrons is. Here is a graph representing electronegativity differences or electronegativity values. So here's fluorine. Fluorine's at the top of the class with a 4.0. The most electronegative element. The noble gases are not included in here because they pretty much don't form bonds, and electronegativity has to do with attracting electrons in a bond. So we left them out of there. So fluorine's the most electronegative, and as you go towards fluorine, in general, electronegativity increases. Again, we can see that hydrogen's got to be a little exception over here. As you go up towards fluorine, electronegativity increases. As you go across from the side, it increases, except for hydrogen. So any questions about that? The way I remember electronegativity is whoever's closer to fluorine on the periodic table is going to be more electronegative. Fluorine has the coolest house. Mm-hmm.
That bond they form.
Right. We're talking about how the electrons are shared in the covalent bond.
Right. So first we were just talking about they were bonding. Now we're talking about more about how they were bonding.
Right.
And you said they were partially negative and partially positive.
Right.
But overall their charge would be what it was as a whole.
Yeah. So all of this is in a molecular compound which has an overall neutral charge.
Yeah.
But what we'll find is that you can have one end of the molecule a little positive, the other end of the molecule a little negative. It's still overall neutral, but one end is a little different from the other. So the electrons are shared, but the sharing is a bit lopsided. And so that makes one end of the molecule different. So here's a model of a chlorine molecule. 2 chlorine atoms, and they're sharing their electrons, and so here's the merged electron cloud. These 2 chlorine atoms are the same element. They have the same electronegativity. The electrons in this bond are shared exactly equally, perfectly equal. And so this doesn't have a dipole moment. It doesn't have one end that's different than the other. Both ends are the same. This is called a nonpolar covalent bond. The electrons are shared, but there isn't one end, there aren't any poles, right? It's non-polar. So what I want you to remember is that any bond between two atoms of the same element is nonpolar. Two chlorines, two hydrogens, two fluorines, whatever. If they're the same, the electrons are shared equally, it's nonpolar. If there's a really big difference, then you actually get an ionic bond, a transfer. So the situation I was describing between hydrogen and oxygen is a bit extreme, and that would probably be extreme enough to be an ionic bond, where the one family actually adopts the child from the other, right? And so then it has a charge, and the other one has a charge as well. That's extreme difference in electronegativity. Ionic bonds are common between metals and nonmetals, because metals have low electronegativity and nonmetals have high electronegativity. So if the difference is big enough, the electron is actually just transferred. In the middle, and there's a lot in the middle, we get these polar covalent bonds. So here's hydrogen and fluorine. Fluorine is more electronegative, so it's hogging the electrons because the electrons are more attracted to it. So this end is a little bit negative and that end's a little bit positive. Polar covalent bonds are very common between two nonmetals. You don't get covalent bonds between metals with anything. Excuse me. Metals are not good at sharing. Nonmetals are better at sharing. So if it works for you, don't be offended by it. But if it works for you, you could think, well, men aren't good at sharing, and women are better at sharing. You see, the man may not share with you, but he'll give you his coat. He'll not ask to share it with you. He'll just give it to you. No, I want you to be comfortable. You take it. So that can be a good thing, too. So we do have some guidelines. It's really a continuum in electronegativity difference between no difference and an extreme difference. The largest difference you can get is 3.3. So how do we decide where on this continuum the things stop? Well, you kind of just have to make a line. So here's where they've chosen to make a line. So if the electronegativity difference is less than 0.4, we call that a pure or nonpolar covalent bond. The sharing is equal or close enough to equal. If the electronegativity difference is greater than 2, then it's an ionic bond, and somewhere in between, it's a polar covalent bond. So that's all very nice, but I can't remember where those lines are, and I don't want to have to look at a table of electronegativity values and subtract to find out what it is. Did I put this on here? No, I didn't. Okay, I need to add a slide here, but I'll write it out for you. So, this nonpolar. So, they call it pure covalent. I prefer the term nonpolar. Nonpolar covalent. How do you know? Same element. If the two elements that are bonded together are the same, it's nonpolar. That's fairly easy to remember. An ionic compound is a metal and a nonmetal. If you have a metal and a nonmetal, it's going to be ionic. The in-between, the polar covalent bond, is when you have two different nonmetals. Like fluorine and carbon. They're both nonmetals. It's a covalent bond. It's a molecular compound, but they're different. There are some situations where you can have two nonmetals that are different elements. They have the same electronegativity. They're having nonpolar bonds. We don't have to worry about that in this class. What I want you to do is look at them. If they're different, it's polar. If they're the same, they're nonpolar. If it's metal and nonmetal, it's ionic. So let's practice. Asking us to identify the bonds between these different elements. If we have iodine and iodine, is it polar covalent, nonpolar covalent, or ionic? It's nonpolar covalent. Because they're the same. And you can kind of think about that. Think about little boys playing, and the houses have equal amenities. There's not one that's more exciting than the other. They're probably going to go back and forth pretty equally. Nonpolar, shared equally. What about between cesium and bromine? Ionic. You look at the elements, you find them on the periodic table. Cesium is a metal. You might not recognize it just from its name, but on the periodic table, we see that it's a metal. It's on the metal side of the line. So this is ionic. We've got a metal and a nonmetal. Phosphorus and oxygen, polar covalent. These are both nonmetals, but they're different. So I want you to say that that's polar covalent. More rigorous method, you should look up the electronegativity, subtract and compare it. And we don't need that in this class, okay? If it's different, it's polar. Questions?
Figure 19 describing, you just said two nonmetals.
Right. So two nonmetals, and they're different. So phosphorus is a nonmetal, oxygen's a nonmetal, and they're not the same. When they're the same, like iodine and iodine, then it's nonpolar. If they're different, it's polar.
Would that also be considered pure covalent?
Pure covalent is nonpolar. So I really should just change that. So pure covalent and polar covalent are different. This is the nonpolar. And I like that word better because it more clearly indicates that nonpolar means no poles. They're the same. Polar means the two ends are different. Any questions? So polar bonds help us to predict whether the molecule itself is polar. If you have a diatomic molecule, it's just two atoms. If that bond is polar, then the molecule is going to be polar. But you can also have things happen where you've got polar bonds, but the whole molecule is nonpolar. And so we need to be able to think about that. A polar molecule has a net dipole moment. We take the polar bonds and we think about adding them as vectors in three-dimensional space, and we figure out, okay, this molecule, one end is positive and one end is negative. Partial charges, it's polar. So I'm going to give you a shorter way of determining that because we don't want to talk about adding vectors in three-dimensional space. So if you have a diatomic molecule, two atoms with a polar bond, the molecule's polar. If that bond is nonpolar, the molecule is nonpolar. Everything's shared equally. When we have two or more atoms, that's where it gets a little more complicated. So here we have carbon dioxide. We previously learned how to predict that this is a linear molecule. Each of these bonds is polar, right? Carbon and oxygen are nonmetals, and they're different. How do we know which one is more electronegative, the carbon or the oxygen? Which one's closer to fluorine on the periodic table? Oxygen. Oxygen's closer to fluorine. The oxygen is more electronegative. This is another notation for indicating a polar bond. The one we used earlier was the D with the posture problem. So the oxygen's more negative, and the carbon is more positive. This arrow, I think of that as like the neighbor who's out weeding the grass, and dad comes home and says, "Where are those kids playing anyway?" And the neighbor points. They're over there. The neighbor's pointing to the house that's more fun, right? So the arrow is pointing to the more electronegative atom. And then we put a plus on the other side so we don't think it's just a regular arrow. This is the positive end, and that's pointing to the negative end. So we have electrons being pulled towards this oxygen. We have electrons being pulled in the opposite direction towards that oxygen. This is adding vectors, right? So a vector going this way and a vector going that way. They cancel each other out. Let's think about playing tug of war. This even looks like a rope, doesn't it? So here's the center of the rope, and you've got a big strong guy over here and a big strong guy over here. They're equally strong. They're pulling in opposite directions. Is the marker on the rope going to move if they're equally strong? No, it's not going to move. They're opposing each other. They're pulling in opposite directions, but nothing moves. This is a nonpolar molecule because there isn't a positive and a negative end. The center is a little positive and each end is a little bit negative, but it's not that one end is different than the other end. Any questions? So we can represent those polar bonds as arrows that point in the direction. If we've got the arrows pointing exactly opposite and they're the same length, then they cancel each other out. The shape of the molecule is important here because water, if we just look at its Lewis structure, we might think it's linear like carbon dioxide and that it's a nonpolar molecule. But when we evaluate it using VSEPR theory, we find out that it has this bent structure. So the oxygen-hydrogen bonds are polar bonds. We have two nonmetals, and they're different. Oxygen's closer to fluorine, it's more electronegative. So this bond is polar with the negative end toward oxygen, the positive end toward hydrogen. This bond is also polar. But now, playing tug of war, we've got two equally strong people, but they're pulling not in exactly opposite, but they're kind of oblique to each other. They're pulling to the side. This is going to move, isn't it? It's going to move this way. So that'll make sense to some of you, and it won't to others. It's okay. You can get past it. Yeah, I don't like that slide. So how do we figure out if a molecule is polar or not? Because we do need to be able to predict this. So this is a more rigorous way. Identify whether it has polar bonds. If it doesn't have any polar bonds, it's nonpolar. Determine whether those polar bonds add together to form a net dipole moment. You have to use VSEPR theory to figure out the molecular geometry. Is the molecule symmetrical, blah, blah, blah. Or we could do this. This is my alternate method for determining molecular polarity. It works maybe 90-95% of the time, which I think is pretty good. And it's easier, much easier. Look at the Lewis structure. You got to start with the Lewis structure. It will be nonpolar if both of these things are true. There are no lone pairs on the central atom, and the atoms bonded to the central atom are all the same, or they have the same electronegativities. I put that in parentheses because it's an important point, but we're not going to run into it. So those are the shortcut rules. So let's do this. Determine whether CH4 is polar. So we need the Lewis structure. So here's the Lewis structure. The shortcut says we're looking to see if both of these are true. No lone pairs and all the atoms bonded to the central atom are the same. Are there any lone pairs on the central atom? No, no lone pairs. Are all of these atoms that are bonded to the central atom the same? Yes. Both things are true. This is a nonpolar molecule. This is a model of that molecule. So if you can imagine the white balls pulling on the black ball, and they're pulling in exactly opposing directions, they're not going to get anywhere. Those dipole moments from the bonds cancel out because of the shape of the molecule. Let's look at this one, NH3. So Lewis structure is needed. Here's the Lewis structure for NH3.
So what are you looking at? It's about just two different nonmetals.
Well, two different nonmetals are going to form polar bonds. So if we look at this bond, that's a polar bond. And the nitrogen-hydrogen over here, that's a polar bond, and this is a polar bond. In order to determine if the entire molecule is polar or not, we have to think about how to add the vectors that represent those dipole moments in three-dimensional space and see if they cancel each other out. Most 3A students don't like to think about stuff like that. In fact, most of my 1A students don't like to talk about vectors in three-dimensional space. Do you like vectors in three-dimensional space? Not especially, no. So my shortcut says, look at the Lewis structure. If there's a lone pair, that tells us that this molecule is lopsided, okay? It's not perfectly symmetrical if there's a lone pair. It's almost certainly going to be a polar molecule now, because here we have the, let me see if I can draw it on here. So here we have the nitrogen is more electronegative, and so we have the nitrogen pulling all of the electron, well, not all of it, but pulling electrons toward itself, hogging electrons. And so this end of the molecule, this nitrogen end, is going to be partially negative, and the hydrogen end is going to be partially positive. There's overall a dipole moment on the molecule. Whereas for methane, where we had 4 carbons, there's not an overall dipole moment. There's not one end that's positive or negative because it's symmetrical. Does that help? A little bit. Yeah. Well, sometimes it's the best we can do. Because there's a lone pair, this molecule's polar. A lot of the things that we're teaching you here may seem like, well, why do we have to talk about that? Well, it's all getting at what kinds of things do you need to be able to understand? Well, this class is a prerequisite for many different things, and so one of the things that's really important in lots of different situations is being able to predict, is this substance polar or nonpolar, because that affects whether things will mix with each other. And that can be really important. Well, you can't understand that unless you understand polarity in bonds, and you can't do that. And you need the molecular shapes, and then you need to know about the Lewis structures, and it all goes back, and that's why we're covering all this crazy stuff. It's building up to specific things. So do you have to completely understand the vector business? No. You can just follow the rules. It'd be great to understand, but it doesn't always work. So SO2. We are short on time, so I'm going to do this Lewis structure fairly quickly. I've got 18 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, that's going to end up like that. Once you have the Lewis structure, predicting polarity, look at the central atom. Does it have any lone pairs? Yep. Polar or nonpolar? Polar. If you see a lone pair, just say it's polar. These are the same element, so that's fine, but it has a lone pair, so it's going to be polar. Oh, I didn't have one of those. We need another example. What about CH3Cl? So the Lewis structure for this one will look like this. Polar or nonpolar? I'm hearing murmurings. Well, let's think about it. What's the central atom? Carbon. Are there any lone pairs in the central atom? No. These lone pairs don't matter in terms of determining polarity. No lone pairs. The next thing is, are all the atoms bonded to the central atom the same or do they have the same electronegativity? This one's different. This is not symmetrical. This is a polar molecule. So now we can talk about why oil and water don't mix. So water is a polar molecule. The hydrogen ends are slightly positive, the oxygen ends are slightly negative. And there is an attraction between one molecule and the next. So one water molecule is sort of attracted to the neighboring molecule, like opposite poles of a magnet attract each other. Those attractions are weak, but they are there. And so that causes the water molecules to tend to clump together or stick together. Oil is not a polar substance. It doesn't have lone pairs, and all of the atoms in there have the same electronegativity, so it's not polar. So it doesn't have that sort of an attraction. So when you mix oil and water, it's a little bit like taking magnetic marbles and regular glass marbles and jumbling them together. You can imagine what happens. The magnetic marbles stick together, right? They're very attracted to each other, and as they're being attracted to each other, they tend to push out or exclude the regular glass marbles because they're not attracted to them. A little bit like cliques in high school, right? You get that clique of girls, and they're just like so stuck on each other, you can't get in there. They exclude you. So oil and water don't mix because water is very cliquish. It's very attracted to itself, it's stuck on itself, and it pushes out nonpolar substances like oil. It's always awesome when I can explain some everyday life sorts of things with chemistry, and this is one of the opportunities. Soap. How does soap work? You probably know from experience that if you get like grease, bacon grease or butter or Crisco or something on your hands, you're not going to get that off just rinsing with water. If your hands are sticky from a soda or a popsicle, you can just rinse it off with water, you don't need soap. But if you got something oil or greasy on there, you're going to need some soap, and you might need a lot of it, right? Because that greasy substance doesn't mix with the water, and so it's not going to be rinsed away. This is an illustration of a soap molecule. So a soap molecule has one end that is polar, and so we've got some negative charge and some positive charge going on here, just some slight separation. The rest of this is nonpolar. So this nonpolar part interacts very well with grease that is also nonpolar. And the polar head interacts with water that is very polar. You could think of polar and nonpolar as speaking different languages. So if you have, I'll pick on the Swedes and the Japanese because my ancestors came from Sweden, my husband's came from Japan. And if you pick on your own ethnic group, it's not, you're okay, right? So imagine a room full of people. Half of them are Swedish, they only speak Swedish. Half of them are Japanese, they only speak Japanese. Are they going to thoroughly mix and mingle and be talking to each other? No. You're going to have clusters of Swedish people speaking to each other in Swedish and clusters of Japanese people speaking to each other in Japanese, right? Because they just don't talk, they can't communicate. It's too hard, right? So they're attracted to people that they can talk to. This soap molecule is a bit like a translator because it can speak both languages. It speaks polar and it speaks nonpolar. Is there another slide? No, I'll have to draw a picture. So what happens is here you've got your blob of grease, right? And then here's the soap molecule. And the soap molecule is going to stick the polar tails into the grease where it'll feel very comfortable because it's all nonpolar. And the little polar heads are on the outside, and those can talk to the water. And so the translator, the soap, will kind of cluster around the grease, and then it can talk to the water, and the water will let it pass. Because here I've got my greasy substance in here, but I know how to talk to you, so you're going to let us through. So it'll break the grease up into some very small pieces surrounded by soap, and then it can get washed away. Has to do with polarity of molecules. Any questions?